Alright, today we're going to look at forces at angles. So we're going to be pulling on a box up at an angle or pushing down on a box at an angle. So if we look at this particular problem, this box is being pulled on a horizontal surface at a constant velocity. That's kind of the key there. So when we pull up at an angle, we're actually pulling with a force in this direction and a force in this direction. So this is going to be the force in the y direction, and this is going to be the force in the x direction. And we first want to know what is the normal force. So this box has weight, and if you notice, if we're pulling up on that box, then if there were a support force pushing up, would it be more or less because we're pulling up on the object? Well, it should be less. Again, you should see that that this vector and this vector is in opposite directions, but these are in the same direction, so the two of these added together should equal the weight of the box. So that's what we're going to do. We're going to say that the weight is equal to the normal force plus Fy, or another way to look at it is the normal force is equal to the weight minus Fy. So how do we solve for the weight? Weight is just mg. It's pretty straightforward. And then how do we solve for Fy? Well, if you remember back when we did vectors, this is just a vector. So we have an angle, and the main force, the resultant, or the hypotenuse, and then we're looking for this side, which is the adjacent side of that angle. So what trig function would I use? Good. So Fy is equal to the sine, or is equal to F times the sine of theta. So Fy equals 125 newtons times the sine of 35.0 degrees. And I get 71.697 for my Fy, and I can plug those two values in up here. And that's what I get. Good to the ones, good to the tenths. Answer's only good to the ones. I'm doing this because I know I'm going to probably have to use it later on. How can I find the force of kinetic friction? So let's look at the forces acting on the box horizontally now. So if I'm pulling with this, then it's a constant velocity. We know that the net force, the acceleration is equal to 0, so the net force is equal to 0 newtons. So therefore the forces in the direction of motion are equal to the forces that are opposing motion. So we have Fx is equal to Fk. So therefore Fk is equal to F cosine theta. Again, this is the adjacent side. And how I'm getting this, just if you need a review, cosine of theta is equal to adjacent over the hypotenuse. So the cosine of theta is equal to Fx over F. So Fx equals F cosine theta. That's how I'm plugging in for Fx F cosine theta. We plug it in, And that's what I get for a final answer there. Mu k. We know that Fk is equal to mu k Fn. So mu k is equal to Fk over Fn. Well, right above we've found Fn, and there's Fk.
Is the camera up here? Anywhere?
Alright, so this is our value for that. Number 2 is going to be very similar, but here just wants you to calculate the coefficient of kinetic friction. So why don't you pause the video and then come back when you're done solving this so you can see if you got it right. So again, you're going to be going through the same process as this one up here, but it doesn't ask you to do each individual step. It just wants this value. So I'm going to do it by all by substitution. Feel free to do this whole process out to get your final answer. Again, pause the video and then come back. Okay, let's take a look at the work that I've got here. First of all, I'm going to put in my forces here. This is called a Freebody Diagram. It shows all the forces that are acting on the system. So I broke the force that's being applied here into a X and Y component, the weight, the kinetic friction, and the normal force. And again, the normal force is going to be less than the weight because we have a force that's pulling up, which assists the normal force to balance the weight. We can kind of see my thoughts here, where the object is accelerating in neither the X nor the Y direction, so the net force is 0. So if the net force is 0, the forces in the direction of motion are equal to the forces that oppose motion, so Fx and Fk are equal to each other. And then in the Y, the normal force is equal to the weight minus Fy. Or you could say the weight is equal to Fn plus Fy and then solve for Fn. That works as well. I did a little substitution where up above we said Fx is F cosine theta. Did that right up here. So I said Fk is equal to that. And then weight is mg and Fy is F sine theta. So I substituted there. I took Fk and Fn. I plugged it into my equation here. I then substituted at that point, showed my addition rule, and then got a final answer of this right here to 3 significant digits. So again, you might have done it each part along the way where you solve for Fk, which would have been 11.5, solve for the weight, which would have been 49 newtons, and then solve for Fy, which would have been 16.4 newtons, and then solve for Fn, which would be 32.6 newtons. So you could have gone that, basically just going through each of these things, where you found the weight, Fy, Fn. Solve for Fk, and then now you have Fn and Fk to solve for mu k. So you could do that, or you could do substitution like this. Either way is fine with me. Let's turn the page. Okay, so this one's a little different. Hopefully you noticed that. This is now pushing down, so again, if we draw on our 2 components there, we have a downward force and a horizontal force. This would be Fy, this is Fx. We still have the weight. But now what's the normal force? Is it going to be greater or less than the weight? Because we're pushing down on the box. Well, the support is going to be greater. Now we're going to look. It says this force is required to set the block in motion. So this is just getting it to start to move. So if that's the case, we have what's called static friction that's now equal to the force that's horizontal. These are now balanced. So I'm going to let you do this problem. It's going to be very similar to the last one, except for we're solving for static friction instead. So I'll let you do that, pause the video, and then come back. Alright, this time I did all the steps out instead of doing the substitutions. So again, you can see I had to solve for Fx and solve for Fy, which would be my components of my force. And again, since it's a 45-degree angle, it's the same value. And then here's where I decide what my normal force is. It's going to be the weight plus Fy. Again, normal force is up, so it's going to balance by the two downward forces, so they're equal to each other. I solved for the weight here, plugged it in. Fy I knew from up above, plug that in. Again, if I look at the addition rule, I'm good to the 10th, good to the 10th, so my answer is good to the 10th, and I actually have 4 significant digits on this number now. And then for us, it's Fs over Fn. Fs is equal to Fx, because again, we talked about that. If it's not accelerating, we're just getting it to start moving, then these two forces are equal to each other. So I took that number from Fx down to here, and then Fn I took from over here to get my mus. Again, it's unitless, and Newton divided by a Newton is a unitless value. Number 4 is a little different. This time we have a net force because it says that it's accelerating. So I'm going to let you kind of figure that out, see if you can do it, and then again, I would draw your diagram here first, unpause the video, see if you got that right, and then if you did, go ahead and start calculating. Go pause the video and then see that. So let's try to do your free body diagram with all your forces first. Okay, here's what I got. I broke this force into its vectors, so Fx and Fy, and then I have the weight. And since we're pushing down, the normal force is going to be bigger than the weight. It's actually going to be the weight plus Fy should balance that. And now since I'm pushing in this direction, I am going to accelerate in this direction, so you can put little swishy lines to show that it's going to be moving here. So friction has to be opposing it, and since it is accelerating, friction is going to be less than the force that I'm pushing with. So I draw the arrow of friction smaller than this component force here. So everybody see how it's smaller? That means that I'm going to have a net force in that direction. Alright, see if you can write down some equations that you know and that you can come up with this situation, and then unpause the video to see if you got those right. Alright, here's the final work for this. So again, I've split it up into x and y columns. In the x column, I know that Fx is F cosine theta, to solve for that. I also know the net force is equal to the forces in the direction of motion minus the force opposing motion. So that's how I get Fx minus Fk. I know that I'm accelerating at 1.50 meters per second squared, so I can determine the net force that's acting on it. I also can find Fx using that equation from up above. And now, with the net force and Fx, I can solve for Fk. So Fk is going to be Fx minus Fnet. Plug those values in, and this is the kinetic friction that's acting on the object. And again, it should be less than Fk. I'm sorry, Fk should be less than Fx. So if Fx is 37.7, Fk is less than that, and it's less by the amount of net force that's acting on it. In the y direction, I have the y component of the force. I also know that the net force is 0 because it's not accelerating vertically. So therefore the forces up are equal to the forces down. So Fn is equal to the weight plus Fy. Find the weight, find Fy, add them together to find Fn. And now I have Fn and Fk, which allows me to solve for mu k.